So today's paper is Protean, VM Allocation Service at Scale. So yeah, by this lovely group of people from Microsoft Azure and Microsoft Research. So yeah, I guess the title actually explains quite a lot about the paper, right? So we're going to be talking about the cloud architectures and how, in this case, Azure allocates the virtual machines and assigns them to physical hardware, right? So I would suspect that many of us have dealt directly with the virtual machines of the cloud provider, be it Amazon, AWS, and their EC2 service, or Azure or Google Compute. So generally speaking, you can pick a virtual machine tier, pick a size, how many cores it will have, what's the RAM capacity, and so on and so forth. Press a button, and this virtual machine magically appears. The operating system is running, and you can start doing your thing, whatever you want to do with this virtual machine. Right, but of course, underneath, it's not as simple as it just magically appearing, right? So we have to have some kind of mechanism to take our request. Hey, I need a virtual machine, and actually assign it to some physical hardware in a data center. Right, so this mechanism will take all of these requests, for all of these different virtual machines at different sizes, different requirements, and so on and so forth, and somehow figure out where, what physical hardware is going to run our virtual machines. So the problem itself is, kind of easily, we can describe it relatively easily, right? So let's say I have this virtual machines that I want to allocate on some physical hardware represented by these 3 server boxes here. And maybe let's say each square represents 1 CPU core, right? 1 virtual CPU of the virtual machine. So if you have this many virtual machines, it's pretty easy to, just go ahead and try and put them in your hardware, right? So that would be one way we can possibly do it. If the only thing that we're constrained about is this CPU size, the square size. So, and this may actually be not a bad way to schedule these virtual machines, because we leave a little bit of slack on every single physical server, right? So that maybe you need the slack, maybe not, but it may be one strategy. However, what if we have another virtual machine coming here that needs this 4 CPU cores? Well, with this allocation, all of a sudden we cannot do anything. But have we allocated stuff? Have we allocated the virtual machines differently? We actually could have, placed this another big virtual machine on the existing hardware, because we do have this 4 empty cores, but they are fragmented, right? So in a sense, this fragmentation at this point disallows us from scheduling more or scheduling this particular virtual machine, even though we technically have the resources. So that is one of the challenges in allocating the resources, or putting these virtual machines into the physical hardware. We want to reduce the fragmentation so that we take we increase the utilization of the cluster. But keep in mind that this is like also a very trivial example here, because I only considered one resource type, which would be this square, the CPU, for example, the amount of CPU cores. But in practice, the allocation will look at more than just the CPU, right? Because when we create the virtual machine, we say, hey, it needs to have X number of CPU cores, this many gigabytes of memory, maybe this much of on-server storage, maybe this much of network bandwidth, and so on. So in practice, like, this problem becomes way more complicated because we do have more things to consider. when we allocate and place these virtual machines. So at Azure, they deployed this system called Protean to manage all of the virtual machine allocations. The Microsoft Azure as a cloud service consists of multiple regions, and each region may consist of one or more availability zones, and each availability zone is going to have a single instance of Protean. And inside the availability zones, you may have multiple data centers, like one or more data centers, and inside each data center, you have potentially hundreds of different clusters, right? So, and to give the scale, like each cluster can be hundreds to thousands of machines. A data center can be thousands to like tens of thousands servers. The availability zone can be up to like 100,000 physical servers, machines. So, and all of these 100,000 physical machines are managed by this Protean VM allocation service. A few interesting numbers that kind of drive the design decisions for Protean, like in terms of like how well it needs to perform, what are the expectations. So in I'll start with figure 4. So in figure 4 right here on the right hand side, it pretty much tells how many requests for virtual machine allocations can happen in any given second, right? So the throughput in terms of virtual machine allocations per second. And normally it's pretty small, right? So here we can see like at night, right, 0 to like 8 morning time, it's probably hovering around 200 requests per second, 200 virtual machine allocations per second, plus or minus. But occasionally it can spike, and on these spikes you can have up to 2,000 requests per second. So in a sense, like in that particular time, at that particular second, you have to find, well, the Protean has to find place for 2,000 plus different virtual machines. So that's kind of driving one of the design decisions for the Protean in the sense that it needs to be able to scale to handle spikes like this, right? So that's one of the design decisions. Another interesting thing that greatly impacts the design is they call it a reuse distance here, but really what this figure shows is how many repeating requests you have, right? So, so by the reuse distance, they say that if someone submits a request for a virtual machine of type X, how many other requests are going to come in between the second request for the same virtual machine X, right? So the number 0 says that if someone submitted a request for this virtual machine of type X, then like in 80% of the 80% of the times, the very next request is going to ask for the same virtual machine. And then in this 4 or 5% of the times, there will be one other request for a different virtual machine before someone else again asks for virtual machine X. So there is a great degree of repetition in terms of what virtual machines are being used, and that is largely because of well, a lot of the virtual machines. Like there are certain very popular types of virtual machines, and certain types are less popular. So people will allocate more popular types of virtual machines more often. Well, furthermore, Protean is not only the public kind of facing virtual machine allocator, it is used for all the other internal services at Azure that rely on virtual machines. So if some internal system asks for virtual machines, well, it's likely it will ask for the same type of virtual machines and quite a few of them. So this again like drives this repetition that we keep allocating the same time to virtual machine over and over and over again. Some other interesting numbers are like this daily pattern, weekly pattern fluctuations. So obviously on Sunday, people tend to allocate fewer virtual machines. And it seems like they work hardest on Thursday. And yeah, the type of virtual machines, it's interesting to see that most of them have just two cores. So they're not like most of the virtual machines are not big at all. But there are a few, there is quite a few of them, I guess also depends on the data center, that have like 20 and more cores. So, very highly, some very highly popular types and sizes of virtual machines, but quite a lot of difference as well. So yeah, like given all of that, right? The fact that we need to, pack these virtual machines into the physical hardware, we need to reduce the fragmentation so that we can park them more tightly, and we need to take into account all of the resources and variations. Well, that becomes a hard problem. In fact, it is NP hard problem. So, potentially we can be screwed with that. So clearly, you cannot solve this problem in a brute force straight approach by just trying all possible combinations of placement, right? What does Protean use? It's kind of a heuristic approach, but it's also almost like a divide and conquer approach. So the heuristic side is really based on this notion of rules. So in order to decide which physical hardware is going to host a particular virtual machine, a particular request to a virtual machine, the requests kind of go through a pipeline of different rules. So there are different types of rules. Some are called validator rules, and some are preference rules. And each type of rule can either be like further subdivided into a cluster rule or a machine rule. So cluster rules, they kind of try to narrow down and focus on the cluster size, the cluster as a unit of allocation, right? So when you create a virtual machine, it will have to go to some cluster and then to some node, to some physical machine in that cluster. So the cluster rules try to narrow down the clusters that we can use for particular virtual machine allocation. The validator rule is pretty much checking whether the cluster can accommodate a particular request for virtual machine. So, for example, if we have a cluster that has no GPUs in it, and the clusters are uniform, so like all the physical machines in the cluster, they are exactly the same, right? So if we have a cluster that has no GPUs in it, but we try to allocate a virtual machine that needs a GPU, then we can clearly disregard the cluster, all the clusters that have no GPUs, right? So similarly, if you're trying to allocate a virtual machine that maybe depends on a specific type of CPU, right? Specific generation, then you can right away discount all the clusters that have different CPU models or CPU generations. So this validator rules on the cluster size allow us to filter out a lot of candidates that are not really candidates for this particular virtual machine. So from considering 100,000 physical servers in a availability zone, you can narrow it down to a few thousand machines, more or less, right? So like you really reducing the scope of your problem greatly just by applying these rules and figuring out which clusters cannot hold that particular virtual machine type. So After the validator rules on the cluster size, you have this preference rules, which more or less rank the clusters based on some nice-to-have parameters, right? So, for example, maybe it's nicer to place the virtual machine in an empty cluster to keep the load balance, right? So by ranking these clusters, Protean comes up with the list of 8 to 16 clusters out of the entire data center that can potentially host this particular VM. And then from this list of clusters, they pick a cluster and just zero in and start looking at the machines. So when they start looking at the machines, they really look, they go through the second set of the rules called machine rules. And again, the machine rules have the validator rules, which are designed to filter out the virtual, the physical machines that cannot host your VM. So one example would be is that like if you're trying to allocate a virtual CPU VM, and you have a server that has only 2 unallocated cores, well, that server is not like it cannot host this VM, so you can filter it out right away. Like you don't have to even consider this server as something that you need to worry about. So again, with the validator rules, they have this few thousand servers that they can potentially place the virtual machines into, and they filter out all the machines that are like guaranteed to not be able to support this virtual machine. In the remaining list of the physical machines, again they apply this preference rules, which are nice to have features and attributes. So, for example, it may be nice to have a machine that has more RAM available, or underutilized machine, or maybe your VM is asking for some specific location for fault tolerance. So this may be expressed as this nice to have attribute. Okay, so all of this work of applying all these rules and filtering out all of these machines and ranking the clusters and the machines happens at this component they call allocation agent, or AA for short. So this kind of illustrates the process in this rather sequential way, right? So you start with all the clusters, you apply the cluster validator rules, you filter out all the clusters that cannot support your particular virtual machine. You have the list of able clusters, then you rank them, and then you maybe pick the highest ranked set of clusters, and you look at their machines, their 10, 20,000 machines, or whatever, 2,000, 3,000. You apply again the validator rules, but now on the machines, to come up with the set of the machines that physically can accommodate the virtual machine. And then you use these preference rules to kind of figure out which one is the best one, which one has the best combination of nice to have features. You eventually will arrive to a set of candidate machines. Maybe you look at like X number of machines with the highest preference score, and then you can pick one trend, for example. So this is where things actually get a little bit confusing for me, to be honest. I do quote the paper here a little bit. So each preference rule, like when we sort them out based on nice to have features, it produces a score, right? So the score SR for like object would be, let's say, a machine, like, or a cluster. A V is the VM. So given a particular VM, you create a score for this particular preference rule, right? And then this score is used to compare the objects, which are clusters and servers. And this comparison, this is how they implement the actual like rules. So each rule has to have this compare method, which takes two objects, let's say two servers, and a particular request for the virtual machine. So like that request would be the set of all the attributes you want in a virtual machine, all the features. And so yeah, this compare function is just going to rank them, right? Order x and y. Tell okay, x is greater than y, same as y, or less than y, based on the score. So just compares them by the score. But the interesting thing is they do not really. So they take the scores from all the preference rules, and they then kind of combine them to make one single score, right? And what's interesting about this score, it's like all the rules are weighted. So each preference rule has some weight W that shows how important this particular nice-to-have feature is in regards to our virtual machine allocation. So they take this weight and they make sure that this weight imposes a strict order between the preference rules, such that effectively any rule can only express a preference among objects that have been preferred by the previous rule. So there is like a very strict hierarchy of preference rules. So if you have an earlier preference rule that is preferred, then that has high score, then all of the servers that have low score on the same preference rule, no matter what other preferences they have, just by because of the weight component, they will never have the combined score greater than the ones that have the higher ranking preference rule set as high. So, but they still compute this kind of sum score. So this is kind of confusing to me, because why do you need to compute this sum score if all you need to do is look at what's the highest weight metric, highest weight preference rule, evaluate it first, get the list of servers if you have enough, then you don't need to evaluate any lower preference scores, lower preference rules. But somehow they still evaluate all of them, and they sum them up and come up with this combined compare function, all the preference rules. But to me, it seems like a waste of work. So most likely I misunderstand something. Anyway, this is kind of how a single AA component works. But if you remember, we need to scale the system, right? We need to make sure that it can handle the spikes in request allocations. So Protean actually uses multiple AAs to provide this horizontal scalability. So they can create more AAs and handle more requests, because each allocator essentially is going to work kind of independently of each other. So, and to support this, of course, they need to be able to store the state of the entire cluster, right? Not cluster, the state of the entire availability zone, like all of the physical machines and what has been allocated to them in some centralized store, because they all need to like draw from that store and figure out which machines are empty and which machines are not empty, and how how much stuff is allocated on each machine to compute all of these scores. Right. So there is a underneath placement store that keeps track of all this placement information, assignment of virtual machines to the physical server, so that you can figure out and compute all of these scores. So, and because these allocators they are independent, like despite drawing from the same database, that they kind of do it in parallel, right? So it's possible that multiple allocators will receive a similar enough request to a virtual machine, run through their scores and that validator preference pipeline, and essentially come up with a very similar set of candidate machines, and then pick the same machine. And if they do so, it may happen that that particular machine is, for example, over-provisioned, because now you have two requests going to two machines versus one. So there are some potential for conflicts when you have multiple allocators running. And the Protean uses several conflict prevention and resolution strategies, which I'm not going to go into that much, at all, rather. But the idea, some ideas are, this is why you pick a random node from the list of candidates, to try to spread it out and make sure that the conflicts are less frequent. You sometimes the placement store is capable of merging the conflicts if they are allowed. So, for example, if you have a conflict in allocation, but the server can handle both of these allocations, then the placement store can combine the two together and proceed with the actual placement of the virtual machine. So there are a few strategies. And finally, because computing all of the scores is expensive, Protean relies heavily on caching, right? So each AA maintains its own cache, because as I said in the beginning of the presentation, a lot of the requests are very similar. So if you computed all of the scores, all of the weights, all of the preferences, and so on, for all of these servers for one request, the next request is going to produce almost identical set of candidate machines, because not a lot of things have changed since then. So they cache all of these computations, and every time they want to use the cache, they just update the cache with the freshest information that they can learn from this placement store. So maybe the cache includes some particular server, but that server has been allocated full. So this update is going to come in and say, okay, the server is full, so it's gonna maybe remove it from the cache of the validator rule, so that it's no longer available for you to use. So instead of actually fetching all of this data from the store and computing stuff, computing the scores, they cache and essentially rely on the fact that a lot of the requests are similar enough. And we can discuss more about caching after the presentation. And yeah, so in the end, this is how the actual architecture, the high level, looks like. You have load balancer, so your virtual machine allocation request is going to come to the load balancer. The load balancer will pick one of many possible allocation agents. The allocation agent will likely to use cache to compute the set of machines that good enough, pick one, and try to write it into the placement store. The placement store will see if this is a conflict or not. If it's a conflict that it cannot resolve, essentially it retries. And the paper says that they can retry up to 10 times. But in practice, they rarely do more than 3. Sometimes the conflict can be resolved and go through as a happy path, saves data into the placement store, which then pushes stuff into the publish subscribe system that feeds back into the allocation agent that can update its cache. So this is the mechanism of how the cache is being updated. So it still can be stale because of all of this multiple steps and pipelines, but it is decently recent to try to avoid as many conflicts as possible. And from here, I guess the actual order to provision resources and create the virtual machine can also go into the whatever the component that provisions the stuff. So yeah, the evaluation, it's you can see that this is kind of like a bimodal. It has bimodal performance, right? So if you're allocating something that is very frequent, very popular VM type, most likely you will have all the caches almost up to date. You will not have to do a lot of like learning from this pub/sub system and updating your caches or recomputing the scores. So you can come up with this allocation strategy for the particular VM, in 10 to 50 milliseconds or so. But if you're not lucky, like if this allocation agent is just starting up, it doesn't have cache, or you're asking for some really weird virtual machine that it doesn't have the rules cached yet, then you may you may end up in a situation where you have to recalculate or calculate all of the scores for all of these rules and progress through all of these calculations. In that case, you can easily see just the allocation time and just computing where to put your machine at above 100 milliseconds. And yeah, here we can see that these latencies, they kind of grow with the cluster size, but not like very drastically. Well, this is a log scale, so I guess it is kind of drastic, to be honest. From 1 millisecond to like almost 10 milliseconds for large clusters. But the paper mentions that they're not really concerned about the latency that much. They just hope that smaller latency allows each allocation agent to handle more throughput, so they can have fewer allocation agents, so they can have fewer conflicts, so that they can have better service again. So yeah, and finally, this is the memory footprint, mostly from like using caching stuff for allocator agent. So yeah, up to 10 gigs of memory for large clusters. So definitely something that's manageable on a good hardware. That's all I have.